All right. Welcome to today's class. All right. We're going to be looking at exothermic and endothermic reactions today. All right. But just before that, there are a few things I need to present onto you as a background, which is necessary as a prerequisite for your understanding of the subsequent things that will be put across to you in today's class. All right. Now, it's important you know that energy changes occur in chemical reactions as reactants change to products. As reactants change to products in a chemical reaction, energy changes occur. All right. Now, this is because the reactants and the products of a given chemical reaction they possess different amount of chemical energy. So because of the different amount of chemical energy possessed by the reactant and the product, that is what gives rise to energy changes. Now, it's also important to note that we cannot measure the amount of chemical energy present in the substance. This chemical energy present in the reactant and the product, it's not easy to actually measure it, directly measure it, all right? So, but we can only observe the energy changes, yes, all right, that accompany the chemical reaction. Now, these energy changes could be in the form of heat. These energy changes could be in the form of light and heat. All right. What I'm talking about energy is in the form of heat. If you look at the reaction between an acid and a base, you will discover that there is an observable heat change. All right. The vessel becomes a bit hot in that kind of reaction. All right. The energy can also be observed in the form of light and heat, like I said. Can also be observed in the form of sound and heat. Example: when you are reacting hydrogen with oxygen. When hydrogen with oxygen is ignited, all right, you will discover that there is a sound. There's a pop sound, all right. So that could also be used to observe the energy changes. It is important to note that all energy changes involves heat. All the energy changes involves heat. Yes. So the energy change we're going to be looking at will be in form of heat. All right. So on the strength of this understanding, this leads us to heat content of a substance. Heat content of a substance. So heat content of a substance is the internal energy which is due to the structure and the physical state of that substance. So the internal energy present in a substance due to the structure and the physical state of that substance is what we call the heat content of that substance. Heat content is also called enthalpy. Heat content is also called enthalpy. Important to note that the heat content can also be denoted by H. Can be denoted by H. Yes. And that is enthalpy. You can denote that. And remember that you can't measure or directly determine the heat content or enthalpy. Heat content. You can't directly measure the enthalpy or the heat content of a substance. So now in a chemical reaction, heat energy is either absorbed or evolved. Heat energy is either absorbed or evolved. All right, and the ability, the absorption or the evolution of heat energy in a chemical reaction is because of the heat content of the substances. Because the heat content or the enthalpy of the substances. All right, and these substances could be, when I say substance, I'm talking about the reactants or the products, all right, involved in the chemical reaction. So because the heat content or the enthalpy of the reactant and the product involved in a chemical reaction is different, because it is different, all right. This is why you have absorption and evolution of heat, because the heat contents are difference. Now, on the strength of this understanding, will further lead us to what we call the heat of reaction. The heat of reaction. Heat of reaction. The heat of reaction denoted by delta H. Remember, heat content is denoted by H. Heat of reaction is denoted by delta H. This heat of reaction is simply the energy change. The energy change. Heat of reaction is also called the change in the heat content. If you don't want to call it heat of reaction, you can call it change in heat content. Change in heat content. Delta H. And you can also call it energy change. You can also call it energy change. All right. So the heat of reaction is the energy change which accompanies a chemical reaction. Yes, it is the energy change or the heat of reaction, which is delta H, is regarded as a constant carried out under fixed set of conditions. All right. It is also called enthalpy change, like I've said, denoted by delta H. It's important to note that I said you cannot easily measure the heat content of the reactant and the product. All right. You can't easily measure the heat content, but it can be observed. All right. Due to heat, light and heat, sound and heat, and the rest of it. But the energy change in a chemical reaction can be accurately measured using a calorimeter. So the calorimeter is an instrument used to determine the accurate values of delta H. Accurate values of delta H is determined using the calorimeter. Now, heat content, enthalpy change or the heat of reaction is a very broad term in chemistry, and it's important to note that the heat of reaction, that's the delta H, in a chemical reaction can be positive. Delta H can be positive. And why can it be positive? If heat is absorbed, and delta H can also be negative if heat is evolved. Heat of reaction can be positive if heat is absorbed. Heat of reaction can be negative if it is evolved. Enthalpy change can be positive if heat is absorbed. Enthalpy change can be negative if it is evolved. And these two conditions is dependent on the heat content of the reactant and the product. Don't get it mixed up here. These two conclusions, these two conditions is dependent on the heat content of the reactant and the product. You are going to get this. This is to say that delta H, that's the heat of reaction, the formula for heat of reaction that I'm presenting to you, is given as heat content of product minus the heat content of reactants. Heat content of product minus the heat content of reactant. It's important we do this because moving forward, I wouldn't be writing the heat content of product this way and the heat content of reactant this way. I would just be writing the heat content of product as HP. So H subscript P, heat content of product, minus H subscript R, the heat content of reactants. Take note of this because moving forward, this is the term I'm going to use to denote this. How to understand this background? This will launch us into exothermic and endothermic reactions because you need to have an understanding of the heat content, heat of reaction, the heat content of substance, the heat of reaction or the enthalpy change before you have a proper understanding of the endothermic and exothermic reactions. Let's start with exothermic reaction. So for an exothermic reaction, a reaction is termed exothermic when the heat content of product is less than the heat content of the reactant. Let me tell you the implication of this. The implication of this is that the heat of reaction or the enthalpy change, which the formula is given by heat content of product minus heat content of reactant, is going to be negative. Why? Because if this value is less than this value, the overall result is going to be negative. All right. So this is one of the conditions that satisfies an endothermic reaction. So you can define an endothermic reaction as a reaction in which heat is evolved to the surroundings. A reaction in which heat is evolved to the surroundings. And when the heat is evolved to the surroundings, it means that the enthalpy change is negative. So, points to note: in an endothermic reaction, heat is evolved. Heat is evolved. Heat is evolved. All right. Heat is evolved also simply means that heat is driven out of the reaction to the surrounding vessel. This also means that the surrounding vessel in an exothermic reaction is hotter than the surroundings. All right, is hotter than the surroundings. Another thing you should note about an exothermic reaction is that there is a rise in temperature. There is a rise in temperature. A rise in temperature. All right, to temperature of the reaction vessel. Yes, that majorly happens in most cases whereby the heat of reaction is large. All right. So this is the example is very practical. For example, all combustion reactions are exothermic reactions because combustion reactions involves burning. Yes, reactions by which a compound or a substance burns in oxygen. All right. So in that kind of situation, you can see that for any combustion reaction, the surrounding is hot. All combustion reactions are exothermic reactions. All neutralization reactions are also exothermic reactions. All right. Example reaction between an acid and a base. All right. That's an exothermic reaction. Displacement reactions too are also exothermic reactions. Now, if you pass an SO3 gas into water, pass an SO3 gas into water, that's also an exothermic reaction because heat will be driven out, enthalpy change is negative, and heat is evolved. All right, that means the heat content of the product is less than the heat content of the reactant. SO3 is sulfur 6 oxide. Sulfur 6 oxide. All right. So let's look at the chart. The energy profile diagram of an exothermic reaction. In the energy profile diagram or graph for the exothermic reaction, you can see how it goes. All right. So this is the summary of the little points here and there we have established regarding an exothermic reaction. Now, if you look at this chart on the vertical axis, you can see here that I have H on the vertical axis. This H stands for the heat content, and on the horizontal axis, we are looking at the reaction parts. All right. Now, this difference is energy, because when we were looking at heat content, I told you that this heat content can be measured as energy, as heat, as light and heat, as sound and heat. So it's energy, and the unit preferably used in this measure is the kilojoules. All right. So you can see here that HR, this is the heat content of the reactant, and this is HP, the heat content of the product. So you can see here that the heat content of the product has a lower value compared to the heat content of the reactant. Yes, that is why you see here that this is less than that, and because of that, delta H, which is heat content of product minus the heat content of reactant minus the heat content of reactant, will give you a negative value. Now, there are other things that is worth noting, because JAM or I could present this to you and ask you to know some parts of this curve. The difference between the heat content of reactant, okay, you can also refer this energy here to as the potential energy of the reactant. So if you don't call it the heat content of reactant, you can refer this to as the potential energy of the reactant. Is the energy of the reactant when it is stable. All right. Well, the difference to now, you can see that this curve rises, it rises, it rises, it rises to a point, and then starts falling to a point before the reaction proceeds through a path. And that part is the part whereby products were formed. All right. Now, this maximum point in the progression of this reaction is called AC, denoted AC, called the activated complex. And the difference between the potential energy of the reactant and the activated complex, that this difference, you can call this, okay, this is better now. This is called the energy of activation. The energy of activation. The energy of activation. This energy of activation is also called the energy barrier, all right? Also called the activation energy. The activation energy is the maximum amount of energy required for a chemical reaction to occur. For a chemical reaction to occur means that this reaction takes a path through which products are formed, because if the reaction occurs, products are formed. So this is called the activation energy. You can also call it energy of activation. This difference. Now, the maximum amount of energy, the peak, this point at which there is a decline, is called the activated complex. Of course, the reactants can be represented as A plus B, that whatever reactants may be, and then the product can be represented as C plus D. Remember, this is energy, this is the reaction part. This is an example. This can be represented, you can see a reaction represented this way. A plus B giving us C plus D, reactant, product. And then you may see something like this, minus 35.0 kilojoules. All right. This value is telling you that this reaction, this is just an example, is an exothermic reaction. It's an exothermic reaction because the enthalpy change is negative. The enthalpy change is negative. That means the heat content of product is lesser than the heat content of the reactant. So this is the summary of the profile diagram of an exothermic reaction. Activation energy, the difference between the product and the reactant, that's the heat content, gives you the enthalpy change. In an endothermic reaction, the heat content of product is greater than the heat content of reactant, and the enthalpy change, also denoted as delta H, enthalpy change, also denoted as delta H, is given as the HP minus HR, and that's positive. Yes, it's simple because this value is bigger than this value. Because of that, the overall result is going to be positive. What's the implication of this? The implication of this is that in an endothermic reaction, heat is absorbed. Heat is absorbed. Absorbed from where? Heat is absorbed from the surroundings. All right. So the surrounding reaction that contains heat, the surrounding atmosphere that contains heat, that heat contained in that surrounding is taken out from that surrounding into the reaction. That means that the reaction vessel in an endothermic reaction is colder than the surroundings. That means that the reaction vessel for an endothermic reaction experiences a fall in temperature. So there is a fall in temperature. Fall in temperature. All right. So heat is absorbed, fall in temperature. So an endothermic reaction is a reaction in which heat is absorbed from the surroundings. And if heat is absorbed from the surroundings, that means the enthalpy change is positive. An example of an endothermic reaction, it's the thermal dissociation of ammonium chloride. It's a perfect example of an endothermic reaction. Ammonium chloride undergoes a thermal decomposition to give ammonia and hydrogen chloride. This hydrogen chloride, not hydrochloric acid. This is gas. All right. And the ammonia, of course, that is gaseous. All right. Ammonium chloride that is in its solid form. So that thermal decomposition of ammonium chloride is an example of endothermic reaction. Now, quickly, let's look at the endothermic reaction profile diagram. Welcome to the energy profile diagram for an endothermic reaction. So it's simple, just like the exothermic, but there is a little bit of difference. So you can see that this is the energy denoted by the heat content. All right, this is the heat content of the product, and this is the heat content of the reactants. So you can see here that the heat content of the product is greater than the heat content of the reactants, and because of that, the enthalpy change is going to be positive, because enthalpy change is heat content of products minus HR. You can see the energy barrier. The energy of activation, which is the activation energy, is the minimum amount of energy required for a chemical reaction to occur. Now, the peak of that activation energy is called the activated complex. All right. And the potential energy of the reactant at this point progresses, gets to a point, and then products are formed. I went through this explanation when I was looking at the exothermic reaction part. Yes. So you could an example. So if the reactant, which is D plus E, when I say D plus E, it could be elements, it could be compounds. producing the product, which is X plus Y. How you know that it is an exothermic reaction? How you know that it is an endothermic reaction? Sorry about that. Is that you will see that delta H will be something, for instance, you'll be given something like plus 25.5 kilojoules, plus 25.5 kilojoules, just for instance. So when you see a positive value for enthalpy change, you will just know that that's an endothermic reaction. Heat is evolved, and because heat is evolved, the reaction vessel is colder than the surroundings. When we say reaction vessel is colder than the surroundings, it doesn't mean that the reaction vessel is very cold. All right, there is a fall in temperature. There is a fall in temperature in an endothermic reaction. So this is a foundational video on endothermic and exothermic reactions. I believe this was of help to you. Drop your questions on this so that I can attend to you better. Thank you. See you in my next class. Alright, so you can like, you can subscribe, and you can hit the notification bell so that you'll be notified whenever I release new videos. Don't forget, learn with master. Alright, so you can share this on all your social media handles, and see you in my next class.